In this video, we talk about the convolution integral, and we start with some motivation in that if we want to take the inverse of a Laplace transform times a Laplace transform, we cannot simply then take the inverse of the first Laplace transform and multiply it by the inverse of the second Laplace transform, because these two are not equal. What we have to do is use the convolution theorem. And the phrase I like to remember to remind me of the convolution theorem is that multiplication in the S domain corresponds to convolution in the T domain. We take some time to look at this convolution integral to understand what's going on, and then we look at properties of the convolution integral. And the convolution integral is often denoted with this kind of asterisk multiplication sign, so it is considered a product, even though this is a product of two functions. So of course it's not like your normal product of two real numbers. It does follow the commutative law, distributive law, associative law, and zero property. It does not have the property that f convoluted with 1 does not equal to f, and also f convoluted with f may be negative. We do some applications of the convolution integral. In particular, we solve some differential equations using Laplace transforms, and then when we have to take the inverse Laplace transform, we need to use the convolution integral. Last, we look at the transfer function and talk about the impulse response of a differential equation. We will start at a beginning where we look at one of the importance of the convolution integral, and that's in taking the inverse Laplace transform. So the Laplace transform is linear, if you recall. So if we have a linear combination of two functions, we can break down the Laplace transform. But what if we need to take the inverse Laplace transform of the product of two functions? So in other words, we have an f of t and a g of t. We've taken the Laplace transform of f of t and g of t and then multiplied the Laplace transforms together. If we want to take the inverse, we can't just say that that will equal to the Laplace transform, the inverse Laplace of f of t and the inverse Laplace of g of t, because, and in fact, this equality does not hold. So this is where the convolution integral comes in. And I want to give you an example of these two cases where we have a linear combination of two functions versus when we have the product of two functions. So this is a problem we have solved before, y double prime minus y prime minus 2y equals 0, and it satisfies these initial conditions. Y of 0 equals 1 and y prime of 0 equals 0. And we're also going to use this formula here. The Laplace transform of 1 is equal to 1 over s. So as we had solved before, we know the Laplace transform of y double prime minus y prime minus 2y. Since the Laplace transform is linear, we can break this apart to the Laplace transform of y prime minus Laplace transform of y prime minus 2 times Laplace transform of y. So this is exactly what is meant by linear. This is a linear combination. In other words, there are scalar multiples which we can pull out, and then terms that are separated by a plus or minus, we can then separate. Using our formulas for the Laplace transform of derivatives, then we convert this here to L of y double prime is equal to s squared L of y minus s f of 0, which is just y of 0, minus f prime of 0, y prime of 0. Then we also have our next term is minus y prime, which is SL of y minus y0, and then finally we have minus 2L of y. So we're taking the Laplace transform here using these derivatives. We group our L of y together, and we have our s squared term, our minus s, and our minus 2. And on the other side, we have y of 0 is equal to 1, so we have a positive s. And then we also have, well, we have y prime of 0, that's just equal to 0, so that goes away. And then we have minus y of 0, so that's minus 1 over here. And so we put it on the other side. So what we get is L of y is equal to, we're going to convert that to y of s being our Laplace transform, s minus 1 over s minus 2, s plus 1. And to make some space, I'm just going to delete these rules here and move these 3 lines up. So here's what I have so far. I don't have a formula for the inverse Laplace transform of something of this form, but I can use partial fractions to break up my fraction into a over s minus 2 and b over s plus 1, and then I can use my inverse Laplace transforms for these 2 forms. So you can look at how I used partial fractions here, and I rewrote my y of s as 1/3 over s minus 2 plus 2/3 over s plus 1. Now when I take the inverse Laplace transform of this, because remember y of s is the Laplace transform of y, which we're trying to solve. We're trying to solve for the y that satisfies this differential equation. So when I take the inverse Laplace transform of 1/3 over s minus 2 plus 2/3 over s plus 1, because the Laplace transform is linear, first I can break apart the 2 terms of my sum, and then I can also pull out these scalar multiples. So I pull out my 1/3 and I have the inverse Laplace transform of 1 over s minus 2 plus pulling out the 2/3 inverse Laplace transform of 1 over s plus 1. And then I use from looking up my table, the Laplace transform of e to the at is equal to 1 over s minus a. So here I have 1/3. Here my a is equal to 2, so that's e to the 2t for the inverse Laplace. And then I have 2/3, and the inverse Laplace transform of 1 over s plus 1 is just this, where s is equal to minus 1. So I'm going to get 2/3 e to the minus 2t. So here is my solution for y of t, the function that solves my differential equation. And just to kind of quickly recap what we did to solve this differential equation, first we took the Laplace transform of both sides of the equation. In order to get this L of y, the Laplace transform is equal to s minus 1 over s minus 2 s plus 1. And we denote that with a y of s. So now we're in the s domain, a function of s. The Laplace transform puts us in the s domain. Then next, since I don't have any formula for the inverse Laplace transform that looks like this form, I used partial fractions so that I could get 2 simpler fractions. So now I have y of s is equal to 1/3 over s minus 2 plus 2/3 s plus 1. And then I used the linearity of the Laplace transform in order, and which also means the inverse Laplace is linear, to break this down, because I have the Laplace transform of e to the at is equal to 1 over sa, which is exactly the form here that I have in my inverse Laplace transforms. And this is what I finally plugged in to get my y of t. We want to compare this situation where we just solved this equation, where our y of s was something that could be broken down using a linear combination, so that we could use formulas to find the inverse Laplace transform and then finally come up with a solution. Well, now what if instead of this y of s, we have something that looks like h of s, which is equal to a over s squared times s squared plus a squared. Well, first, we don't have anything in our Laplace transform that is of this form, but we can take this fraction, the a over s squared times s squared plus a squared, and simplify it to 1 over s squared, so pulling out the s squared. So we have 1 over s squared times a over s squared plus a squared. Now we do have things in our table that match the 1 over s squared. The Laplace transform of t will give us 1 over s squared. And the Laplace transform of sine of at will give us our a over s squared plus a squared. So that's good news. However, I cannot say that the inverse Laplace transform of the product of 2 functions is the product of the two inverse Laplace transforms. In other words, the inverse Laplace transform of 1 over s squared times a over s squared plus a squared does not equal to the inverse Laplace transform of my first function times the inverse Laplace transform of my second function. Linearity does not apply to the product of 2 functions. You can pull out scalar multiples, but not entire functions. And I have this inequality written in the words here. So the inverse Laplace transform of a product of 2 functions, that's this, the inverse Laplace transform of the product of 2 functions, is not equal to the product, so here's the product, of two inverse Laplace transforms. And this is exactly where the convolution theorem comes in. And it says, if capital F of s is the Laplace transform of little f of t, and capital G of s is the Laplace transform of little g of t, then if h of s is the product of the two Laplace transforms of the capital F of s and g of s, again, capital F and g of s are Laplace transforms, then the inverse Laplace transform of h of s is equal to h of t, which is equal to an integral from 0 to t f of t minus tau g of tau d tau. And here tau is just the variable of integration. And that's equal to, so you can switch the roles of f and g. So f can be f of tau and g can be t minus tau d tau. So what the convolution theorem tells us how to do, if we have a function that's the product of two Laplace transforms, then when we take the inverse Laplace transform, we use the convolution integral. The proof is based on the definition of the Laplace transform, if you recall, is just the integral from 0 to infinity e to the minus s. Here we're using the variable c as the variable of integration f of c. And here I have capital G of s, integral from 0 to infinity e to the minus s, and now our variable of integration is tau, g of tau, d tau. I multiply the two together. What I'm going to do is this part of my integral, which does not depend on tau, I'm going to do that part first over here. And once I get my result, so here's my parentheses, once I get my result, I'm just going to multiply that times this inside this integral here. And then in my next step, I'm going to take my e to the minus st and I'm going to combine it with my e to the minus sc right over here. Now inside this integral here, the tau is going to, when you integrate from 0 to infinity, you do that for a fixed value of tau, and then you integrate with tau going from 0 to infinity. But inside here, tau is fixed. So we're going to let c equals t minus tau. So for the fixed tau, so that dc is equal to dt, and epsilon equals 0 means that t equals tau, and epsilon equals infinity means that t is equal to infinity. So now we can substitute in here, so I still have my integral 0 to infinity g of tau, then here instead of 0 into infinity, I get tau to infinity, e to the minus st, f of t minus tau d tau, which is exactly what I wanted to show over here. Now that we've proven the theorem, we're going to go and take a closer look at the actual formula for our convolution, and we're going to start by looking at this formula here, this form of the formula where it's g that has the t minus tau and f just has the tau. And the first thing we will do is look specifically at this t minus tau. As an example, let's say g of tau is equal to sine of tau, so we have this curve here. Then when we take this negative tau, what that does is it gives us a reflection along the vertical axis. So this is what we get here. Or I can think again of reflecting this portion across this vertical axis, and that would give me this curve here. Reflecting this portion here across the vertical axis will give me this here. And then reflecting this across the vertical axis, well, it'll start way over here. And this is what I get. So then my final reflection of this sine curve over the vertical axis gives me this blue curve here, which is exactly what I've drawn over here. Looking at this t minus tau, so this t, this extra term then moves the graph to the right as t increases. So for example, if we have pi over 4 minus tau, that would give us sine pi over 4 minus tau. So in other words, we just take each of these points and we move them over. It just shifts everything over pi over 4. So I put the movements of this g of t minus tau, both the reflection and then the shifting over here. And now I've drawn a curve that I'm going to use to represent f of tau. And next, I was going to use this cosine wave as my g of tau, but then I realized just it would be easier if I only used the portion that is positive above the x-axis, just so I don't have to worry about different areas canceling out. So here, well, I guess it still is a portion of the sine wave. This is going to be our g of tau. And then it's also kind of nice because the reflection across the y-axis is already done for us. I've moved my graph of g of tau and f of tau up so that underneath I can plot my graph of h of t. Remember, h of t is just a function depending on t, so we can graph h of t. We can look at the convolution as t evolves. We'll start graphing h of t for some discrete points, and we'll start at t equals 0. So h of t is this integral here, and what you notice is wherever f of tau, g of tau, the black function, and here t is equal to 0, so t is 0, so all we get is g of negative tau, which is this curve here. Wherever it is non-zero, we see that f of tau, the blue function, is actually 0, and I'll emphasize that by graphing the 0, the curve, and then the 0. So this means whenever, and then over here, when f of tau is non-zero, we see that our g of tau is equal to 0. So this product here is always 0 for t equals 0. So at t equals 0, our convolution, h of t, is going to be 0. For my next point, I could get to pi over 4, but you know what? I'm just going to skip over a little bit, and I'm going to look at the point pi over 2. So in other words, I want to calculate h of pi over 2. And by my formula over here, what I need to do is then integrate from 0 to pi over 2 f of tau times g of pi over 2 minus tau d tau. Then looking at this g pi over 2 minus tau, that means I need to shift my g function over by pi over 2. So I'll do that next. I'm going to shift this over pi over 2. And now when I look, I'm integrating from 0 to pi over 2. And here, there's still, let's see, whenever my g function is non-zero, my f function is still 0. So actually, this is pi over 2 is just fine. I'm still at 0. If for my next point, I want to look at pi, so h of pi, integral 0 to pi, f of tau, g of pi minus tau. And the next thing I'm going to do then is to shift my function g over by pi. So you can see we have this maximum overlap. The next step now is to multiply my f of tau and my g of pi minus tau. So somewhere over here at pi over 2, actually that's not, it may be over here, right in between, I see that the height is probably somewhere around a quarter. So a quarter times a quarter would be an 8. At pi, I have the height at 1. So multiplied together, I get 1. So probably my curve for multiplication looks a little bit like this, something in yellow. So now I have the multiplication, and now I need to integrate from 0 to pi this multiplication of the two functions, but the integration is really just the area underneath the curve. So this is where my function, my tau is. It's the area under the curve. I don't know how big it is, but you know, my h isn't scaled, so I'm just going to say that it's something positive, and at this point at pi, we'll just put it over here. I'm going to choose my next point as 3 pi over 2, so first I need to shift my g function. So I'm going to move that over here. I'm going to look at the area that I'm integrating from 0 to 3 pi over 2. And now I need to do my multiplying, and here I'm just going to cheat, but I'm going to say, here at maximum, we're something a little under 1 times something a little under 1, so that's going to be even smaller. But we're going to get kind of this area here, and again to 3 pi over 2. But it was definitely, just looking at this, it was definitely smaller than this area over here. So now we're decreasing again. Just kind of put it here. And just to note, again, over here, this g function is 0, which is why none of this contributes to our h of t. The next point I will do is 2 pi. So first I'm going to shift my black over to 2 pi. And again, if you look at this, again, this is going to be 0 because wherever this black curve is non-zero, the blue curve is 0. So there's no overlap again. And from here on out, my curve is going to be 0. So it's non-zero, it's going to kind of creep up, it's going to creep back down, and then it's going to be 0. So now we have a graph of what h of t is doing. That's what this integral is doing. That's what this g of t minus tau is doing, is shifting everything. And one thing to notice is this maximum here occurs, when there's maximum overlap between g and f of t. And with that comment that our maximum had come when there was maximum overlap, if our f of t had been something like this, a different frequency, the area of overlap is much smaller. So, for example, when we calculate h of pi and we integrate from 0 to pi, over here, our f of t, there's not as much space where the two functions are both non-zero. And then when we calculate this, we still have to multiply. We get something a little bit shorter, and we might get some curve like this. So our peak would have been smaller. So this graph would be something much shorter. And the idea is because since the graphs don't have as much overlap, they're different frequencies, we're going to have a smaller h, a smaller convolution. So one of the important points about convolution is it tells you the degree of overlap, and convolution reaches a peak when f and g overlap the most. Before we work some problems, I just want to give you this phrase here because it helps me remember how to get from here to the convolution. And the phrase is multiplication in the S domain corresponds to convolution in the T domain. So in other words, S domain, that's because when you take the Laplace transform and you integrate with respect to S, you end up with variables in S. So you're in the S domain. You move from the time domain to the S domain when you do the Laplace transform. So when you multiply in the S domain, what that corresponds to is this convolution in the T domain. In other words, that's equal to the Laplace transform of H, where H is the convolution. It's not simply the product of your two functions. This is a not equals. So again, the phrase I like to remember that helps me remember what to do is that multiplication in the S domain, here, corresponds to convolution in the T domain. And I will use this phrase. I'll show you how I use it in a problem just to kind of remember what to do. We will go back to that motivating example at the beginning of our video, and we'll find the inverse Laplace transform of a over s squared times s squared plus a squared. And just to remind you, we had broken up this h of s into 1 over s squared times a over s squared plus a squared. And we noted that the Laplace transform of t is equal to 1 over s squared, and the Laplace transform of sine of at is equal to a s squared plus a squared. So in this case, f of t, little f of t is equal to t, little g of t is equal to sine of at, the Laplace transform of f of t is equal to 1 over s squared, the Laplace transform of sine of at is equal to a over s squared plus a. Now, if we want to find the inverse Laplace transform of h of s, so we're going to call that h of t, and again, h of s is the inverse of the product of two Laplace transform. So if we want to find the inverse Laplace transform, what I need to remember is that multiplication here in the S domain corresponds to convolution in the T domain. So we will be using the convolution theorem. And here we set up our integral 0 to t, f of t minus tau, g of tau, d tau. So plugging in for f of t minus tau, we get f of t minus tau. For plugging in g of tau, we get sine of a of tau, d tau. Now here, we're going to use integration by parts. I let u equals t minus tau, and my v prime is equal to sine of a tau. I'll let you check my integration by parts here, and then plugging in my limits of integration, I get ta minus sine of at over a squared. And this is it. So this is my final answer. This is the inverse Laplace transform of a over s squared plus a squared. You can also confirm the other half of this formula. So here we used f of t minus tau, g of tau, but we could have used f of tau, g t minus tau. In other words, the integral from 0 to infinity, f of tau, in this case, would just be tau, and g of t minus tau, in this case, would be sine of a t minus tau. You can confirm that this integration will give you the same answer. We've gone through the introduction, and we defined the convolution integral as these two integrals here. And the thing is, this convolution is known as a product. It's a type of product. It's a generalized product and can be written f this asterisk g of t is equal to our convolution integral. If you like this notation, which I don't because this looks a lot like multiplication, but it actually means convolution. But convolution has many properties of an ordinary multiplication. And when I say it's a generalized product, it's a product in the same way that you can have matrix multiplication, which certainly is not defined the same as multiplication of two real numbers, or you can have multiplication of complex numbers or multiplication of vectors. For multiplication of vectors, you had to go to dot product and cross products. So in this way, you have the multiplication of two functions, but it's not your normal product. It is the convolution integral. But we call it a product because it has many properties that we associate with multiplication. That is the commutative law, the distributive law, associative law, and zero property. The properties that the convolution integral does not have is f convoluted with 1 does not equal to 1. And I have this written out here. So f convoluted with 1 is the integral from 0 to t, f of t minus tau times 1 dt, which is the integral from 0 to t, f of t minus tau dt, which is not equal to 1 in many cases. So for example, if f of t is equal to cosine of t, then we have this is equal to 0 to t cosine of t minus tau, which is negative sine of t minus tau, evaluated at 0 and t, which would give us sine of t. The other property that convolution does not have is f convoluted with itself may be negative. So next I have this example of using a convolution integral in solving a differential equation. So we have y double prime plus 4y equals g of t, y of 0 is equal to 3, and y prime of 0 is equal to negative 1. So I have our Laplace transform of y double prime plus 4y. So the Laplace transform of y double prime is s squared L of f of t minus f naught minus f prime of 0. And then we have 4 Laplace transform of f of t. So I can group my Laplace transform of f of t, and I have my s squared, I have my plus 4, and then here I have, well, y of 0 is equal to 3, so minus 3s, and my y prime of 0 is equal to negative 1, so this gives me plus 1. And this is equal to, on this side, I have the Laplace transform of g of t. I'm going to let capital Y of s equal the Laplace transform of f of t. So what I have is y of s times s squared plus 4 minus 3s plus 1 equals and then I'm going to let capital G of s be the Laplace transform of little g of t. So now y of s, moving this over and then dividing everything by s squared plus 4 is 3s minus 1, because I moved it over, divided by s squared plus 4, plus g of s over s squared plus 4. I separate out these two equations, these two fractions, so I have my 3s over s squared plus 4. So I take out my 3 over s squared plus 4. Now I have a minus 1 over s squared plus 4, but I actually, so I can fit this form over here for my inverse Laplace transform, I want a 2 on top because I want this to be a and this to be a squared. So this is 2 and this is 2 squared, which means I need to multiply by 1/2. So this comes from my minus 1 s squared plus 4. I just multiplied by 2 and then multiplied by 1/2. Similarly, for g of s, I factored out my g of s, but I want a 2 on top so that I have my a and a squared form here. So I have to multiply by 1/2. So these two are straightforward. Here I have the form of my cosine of at, where a is equal to 2. Is that right? Yeah, a is equal to 2. So I have 3 cosine 2t. Here I have my form of sine of at, where a is equal to 2, so I have 1/2 sine of 2t. Here I have two functions that I can get a inverse Laplace transform over here, and then I have something else, a g of s, that is the inverse Laplace transform of little g of t. And here I have two Laplace transforms multiplied together. So what we want to remember is multiplication in the s domain corresponds to convolution integral in the time domain. So I have my 1/2. I'm going to integrate from 0 to t. This here corresponds to my sine of at, so my sine of 2t. But now I'm going to use my t minus tau. So this is sine of 2t minus tau. And then I have my g of tau, d tau. At this point, because I don't know little g of t, I can't do much more with this. And this will be my final answer here. And our convolution integral allows us to write the solution of an initial value problem in terms of an integral. And now we're going to look at the general problem ay double prime plus by prime plus cy equals g of t, y of 0 equals y naught, and y prime of 0 is equal to y prime of 0. So this problem is often referred to as an input-output problem. First, the coefficients a, b, and c, they describe the properties of some physical system here. G of t is the input, or the forcing function, and then our y naught and our y naught prime are our initial conditions, or initial state. And the solution y that satisfies this differential equation is the output at time t. I solve as I normally do. I take the Laplace transform of the left-hand side of my equation, ay double prime plus by prime plus cy, and then I multiply a times the Laplace transform of y double prime plus b times the Laplace transform of y prime plus c times the Laplace transform of just y. Now I group all the terms that multiply L of ft together, the terms that multiply by y naught, and then the term that multiplies by y naught prime, and all of that is equal to the Laplace transform of the right-hand side of the equation, which is capital G of s. I let y of s equal L of ft, so then I have this form of y of s is equal to as plus b times y naught, plus a y naught prime plus capital GS all over as squared plus bs plus c. I can break up my y of s into two portions. This first portion, as plus b times y naught plus a y naught prime over as squared plus bs plus c. And this here, the inverse Laplace transform, is the solution of the homogeneous equation ay prime plus by plus cy subject to the initial conditions. In other words, the initial value problem of the homogeneous equation. The second part, the gs over as squared plus bs plus c, the inverse Laplace transform of this is the solution of the non-homogeneous equation where the initial values are set to 0. This first part of y of s, we can find the inverse Laplace transform here using the linear properties of the Laplace transform. This we are going to consider further. I have rewritten the general problem we were considering, ay double prime plus by prime plus cy equals g of t, with initial conditions y naught, y of 0 is equal to y naught, and y prime of 0 is equal to y naught prime. We said that y of s is equal to this fraction here, and we divided it into 2. We said to take the inverse Laplace transform of the first part, the first term, we can just use regular linear properties of the Laplace transform to take the inverse Laplace. What we are going to look at next is taking the inverse Laplace transform of the second term, g of s over as squared plus bs plus c. So looking at the inverse Laplace transform, we often divide this further into hs and gs, where hs is the denominator, as squared plus bs plus c to the -1, and we call that the transfer function. We see hs is dependent only on the properties of the system, that is a, b, and c. It does not depend on this forcing function g of t. On the other hand, g of s depends only on the external excitation, g of t, the forcing function applied to the system. And by the convolution theorem, now when we want to take the inverse Laplace transform of the transfer function times g of s, what we need to do is take the convolution of h of t minus tau, g of tau. And we want to consider the special case where capital G of t is equal to 1, and that'll tell us more about the transfer function. Well, for capital G of t to equal to 1, what we want to recall from the previous video is that the Laplace transform of the direct delta function is equal to 1. So the corresponding function little g of t for capital G of t is equal to 1 is equal to the direct delta function. So now we can look at h of s, the transfer function, which is 1 over as squared plus bs plus c. From our previous slide, we said g of s over as squared plus bs plus c, in this case g of s is equal to 1, so we're left only with our transfer function, is the solution of our y double prime plus by prime plus c is equal to g of t with our initial conditions equal to 0. So in other words, our h of t, then our inverse Laplace of this, is the solution of y double prime plus by prime plus c equals the direct delta with initial conditions equal to 0, which makes h of t the impulse response of the system. In other words, the response of the system when given this unit impulse function as the forcing function. An example of the usefulness or the application of this impulse response is, I'm going to give you an audio example. So if the system you're describing with this differential equation, ay double prime plus by prime plus cy, and remember this part of the equation defines your system, g of t is your forcing function. So if the system, say, is a room, and you want to know how a room will change the acoustics of a sound you put through it. So you are playing a guitar, you walk into a new room, how does the sound change? Well, what you can do is you can put an impulse response through it. You know, this is like what audio people always do, like when they do that really loud clap. They're trying to approximate the direct delta function. In other words, a sudden impulse sound that contains, in this case, as many frequencies as they can manage. Ideally, they get all. If they hit the direct delta function exactly, they would have all the functions, but of course the direct delta isn't ideal. But anyway, they try to approximate the direct delta because that contains all the frequencies of the spectrum. So when they do this convolution, then they'll know h of t will give you the response. And when you feed in the direct delta, it gives you the response of all possible frequencies. And from that, you can predict how any audio going through that room will sound. And that is my example for you of this impulse response and this convolution. Now, considering our transfer function, we're going to look back at the previous example where we found the solution of y double prime plus 4y equals g of t, where y0 is equal to 3 and y prime of 0 is equal to -1. As I had mentioned, we had done this problem already in a previous slide in this video, but I have the work done here, which you can take a quick look at, and this was the solution. And you might recall the solution because we left this, since g of t, our forcing function, wasn't given to us, we left the solution in terms of our convolution integral. Looking at this problem now in regards to the transfer function we had just considered, this part of the problem, this part of y of s, it's easy to take the inverse Laplace transform using the linear properties of the Laplace transform. Here is where we have our g of s, our impulse function, the Laplace transform of our impulse function, times our transfer function. So h of s, our transfer function, is equal to just the 1/2, 2 over s squared plus 4, or canceling out the 1/2 and the 2, I get 1 over s squared plus 4. So here, if I take the inverse Laplace and I get lowercase h of t is equal to 1/2 sine of 2t, this is our impulse response. And remember, it's the impulse response because h of s is our transfer function that we get when we assume capital G of s is equal to 1, which means the inverse Laplace transform of g of s would equal to the direct delta function, which makes little g of t the direct delta function, which is a unit impulse. So again, this h of s here then gives us our little h of t, gives us our impulse response. This is what happens when we put an impulse response into this system. And then similarly, this other part here was the solution to the homogeneous equation with initial values. I am going to work 3 more problems for you, and this first one I'm going to do a little differently because this problem is not about calculations, but it's really about thinking about this convolution theorem and how it all works and how the inverses work, etc. And I don't want to just show you how to do the solution because that really defeats the purpose of the problem, which is that you should be thinking about it. So I'm going to give this problem to you now, and then I'm going to encourage you to pause and think about it. If you don't get it, go ahead and finish the rest of the video, do the other problems, maybe even sleep on it. But the very last problem I do before the review will be to show you the solution. But I will say this problem exactly follows this convolution theorem, and if you understand all of these 2 lines here, this problem should fall out. So again, pause the video, give it a try, and I will not answer it until the very end, right before the review. My next problem is to find the inverse Laplace transform using the convolution theorem of 1 over s to the 4th times s squared plus 1. I've decided when I see this is the product of 2 functions that I'm going to lay out my work so the convolution theorem falls out pretty easily. So I'm going to use my notation. I'm going to call this h of s, and it's the product of 1 over s to the 4th times 1 over s squared plus 1. So I'm going to suggest you kind of follow this notation as well. When you see the product of 2 functions, call it h of s. That way it's consistent with, it'll fall right out. This formula will fall right out of the convolution theorem. So here I can see, I look up on my Laplace table, and I see that the Laplace transform of n factorial over s n plus 1 is equal to t to the n. So I have something roughly equal to that, and I'll show you why I say roughly equal to that. Here I see that this, by the Laplace transform, follows the form for the sine. So I say that f of s now, which I'm going to remind myself, and if, I think this is an extra step, but I would encourage you to write this as well on your solution. So capital F of s is the Laplace transform. Remind you that this is little f of t is equal to 1 over s to the fourth. And I'm going to use this formula from my table, and I'm going to say then that f of t is equal to 1 over 3 factorial t to the third. So you can take a look at this, compare. And I would write this out, this L f of t and this f of t. So similarly for g of s, that's the Laplace transform of g of t is going to equal to 1 over sine squared plus 1, which implies that g of t is equal to sine of t. Now everything should fall out easily from the convolution theorem. From the convolution theorem, this line here, the inverse of h of s, which is exactly what we were asked to find, the inverse of this function, is equal to this convolution integral of f of t minus tau. So I plug in t minus tau for t times g of tau. So I plug in my tau in sine of t. So this is my solution right here. So as I was trying to figure out how I was going to lay this out in order to explain, I settled on writing this out. And I highly suggest you do this because I realized after writing it out this way, having this convolution theorem here, it's just easy to plug everything in. And I feel like the solution just falls out for you. This last problem that I have for you has a little bit of everything. So express the solution of the initial value problem in terms of a convolution integral. And the initial value problem is y double prime plus y prime plus 5/4 y equals 1 minus this unit step function at pi. Y of 0 equals 1 and y prime of 0 is equal to -1. Taking the Laplace transform of both sides of the equation, here I have the Laplace transform of y double prime, the Laplace transform of y prime, and then 1/4 the Laplace transform of y. And over here I have 1 minus, and I use this formula for my table of Laplace transforms. I get 1 over s e to the minus pi s. I just realized I forgot to take the Laplace transform of 1 over here. So I need to take the Laplace transform, and this side becomes 1 over s. So I'm sorry, I have to redo this. So my y of s times s squared plus s plus 5/4, these two cancel out, give me, is equal to moving this s over plus the 1 over s plus 1 over s e to the pi s, which means ys is equal to s over s squared plus s plus 5/4 plus 1 over s times s squared plus s plus 5/4 minus the e to the minus pi s over s times s squared plus s plus 5/4. And now to look at my table of Laplace transforms, I have a bunch of stuff with sines and cosines where we have the denominator equal to something like s squared plus a squared. So I need to use completing the square for this s squared plus s plus 5/4. So I get s plus 1/2 squared plus 1. So I converted all of these fractions using completing the square. And now I can look at these. I'll look at these one at a time, but they look something of the form e to the at cosine of bt or e to the at sine of bt. In particular, if I look at this looks sort of like this form here, e to the at cosine bt, because I have my s. So I need to introduce my minus a, and I can do that because later I'll just add something with a plus a. This form looks a lot like b over s minus a squared b squared, and then I also have times 1 over s. So here's where I'll use the convolution theorem. Here, this one's looking a little more complicated, so you know what? I'm going to defer that and think about that after I get these two done. For my first term, then, I said I wanted to get it into the form of s minus a over s minus a squared plus b squared. So I'm just going to go ahead and throw in the 1/2 here. But in order to do that, I need to subtract a 1/2. So this is what this term is right here. It's my subtracting the extra 1/2. This term, I just separated out the 1 over s from the 1 over s plus 1 squared plus 1. So I know how to take the inverse Laplace transform of 1 over s, and I know how to take the inverse Laplace transform of this form here, this b over s minus a squared plus b squared. And then last I said I was going to defer this, so I separated out my e to the minus pi over s from the 1 over s plus 1 squared plus 1, and I kind of chose to do this separation because this I can see is the inverse of 1 over s minus a squared plus b squared. And so I was going to look and see what this would give me if I just separated this out. And luckily, this here, or fortunately, except maybe not so fortunately because it's a textbook problem, this here, I know this is of this form here, the 1 over s e to the minus cs. So I'm in luck with this. So I do have these two terms here. Both will need to use the convolution theorem. When I take the inverse Laplace transform of these two terms using these two formulas here, I'm just going to note that a is equal to minus 1/2, b is equal to 1 for both terms. So I get the inverse Laplace transform here. I've got this form, so I have e to the minus 1/2 t cosine of 1 times t, and this is 1/2, minus 1/2, and then I have the sine form, so e to the minus 1/2 t sine of t. I'm going to take the inverse Laplace transform here using convolution. And to give myself more space, because I want to be really clear exactly what's going on, I'm going to clear all this stuff out here and just move this up to the top. Here is the last line from the previous slide, and now I have more space so I can work on the convolution of these two terms. Working on the convolution of my first term, which I'm going to call h of s, so that's 1 over s, 1 times 1 over s plus 1/2 squared plus 1. So I wrote it again in terms of h of s, so everything will easily fall out of my convolution theorem. So my h of s is a multiplication of two functions. My first function I'm going to identify as f of s, and I just write this out so everything falls out nicely. F of s, to remind myself, is the Laplace transform of little f of t, and it's equal to my first function 1 over s, which implies, using my formulas here, 1 over s implies f of t is equal to 1. Then from here I get g of s, which is the Laplace transform of little g of t, is equal to 1 over s plus 1/2 squared plus 1. Using my formula over here, that will imply that g of t is equal to, what is this? Yeah, e to the minus 1/2 t sine of t, where a is equal to 1/2 and b is equal to 1. Which means from my convolution theorem that h of t, which is the inverse Laplace of h of s, is equal to 0 to t. And I chose to use this form because f of tau, this is so easy because f of tau now is just 1. And then my g of t minus tau would be e, and then plugging in t minus tau for t, to the minus 1/2 t minus tau, sine of t minus tau d tau. I do the same thing for my second term, this e to the minus pi s over s times 1 over s plus 1/2 squared plus 1. I rename that as h of s, and I want to figure out the convolution of h of s. So my first function is equal to my capital F of s, which is the Laplace transform of little f of t, which is equal to e to the pi s over s. And actually this should be minus pi s over s. So there's a minus sign in there. And that will imply that f of t is equal to u using this formula here, right? So I have e to the minus pi s over s. So c is equal to minus pi. Oh, so this is actually u of pi, because this is a minus, u of pi of t. So I can get rid of this minus here. This came because I had dropped the other negative sign. And now my g of s is actually the same as my first term. So I can just bring all this down. So g of s is equal to 1 over s plus 1/2 squared plus 1. That means g of t is equal to e to the minus 1/2 t sine of t. So now I can find h of t, which is the Laplace transform of h of s, is 0 to t, this step function, at pi of t, e to the minus 1/2 t minus tau sine of t minus tau d tau. It's really too bad I'm at the end of my page right here because I only had one more line to go. But you know what? I'm going to get rid of this intermediate step and this intermediate step, move some things up, just so I can write the final solution just to be complete. But really the solution is, you already have it. It's this plus this, and instead of this term, we just plug in this, and instead of this term, we just plug in this. But I'm just going to write it for completeness sake. And this here then will be my final answer for y of t that solves this differential equation. To summarize our video now, we talked about taking the inverse Laplace transform of the product of two functions. We cannot simply assume that the inverse Laplace transform of the product of two Laplace transforms would equal to the product of the inverse of the two Laplace transforms. Instead, if we had two functions that were Laplace transforms of little f and t and g of t, then when we let h of s equal to f of s times g of s, to take the inverse Laplace transform of h of s, we had to use this integral here, the convolution integral, or the convolution. And that's what our convolution theorem told us, was basically how to get the inverse Laplace transform of a product of two Laplace transforms. You do this, h of s, the inverse, is equal to little h of t, which is this convolution integral. We talked about the convolution integral and what it looked like, what this t minus tau looked like. The minus tau is a reflection across the y-axis. The t shifts our graph over, and then h of t is actually a function. So we could plot that. We could calculate h of t for different values of t, and then we could make a plot of h of t. And we also saw that this convolution gave us indication of how much overlap our two graphs f and g had. We are back to this problem that I wanted to encourage you to try to work out on your own. Again, it's not about calculation, but the understanding you have of this theorem and these two lines. So if you have not given it a day's thought, please pause the video, sleep on it, and then come back and see the solution, which is on the next slide. The first thing to notice is you want to take the Laplace transform of this integral, and this integral is in exactly the same form as the convolution integral. So the first thing I am going to do is just kind of identify my pieces, my f of t and my g of t. Comparing my convolution integral to this integral here, if I make f of t equal to e to the minus t and g of t equal to sine of t, then my convolution, which I will call little h of t, just being consistent with this notation, will be exactly this integral here. I'll have e to the minus t minus tau and then sine of tau, and that's exactly what we have here. The problem is to take the Laplace transform of this integral, so I'm just going to say I want to take the Laplace transform of this h of t. Looking at my Laplace theorem, convolution theorem, and kind of writing what this Laplace transform of h of t is equal to, well, that's equal to capital F of s times g of s, which is equal to the Laplace transform of little f of t times the Laplace transform of little g of t. Using these formulas from my table of Laplace transforms, I can find the Laplace transform of f of t, which is equal to e to the minus t, is equal to 1 over s plus 1, and the Laplace transform of g of t, which is equal to sine of t, is equal to, using this formula, 1 over s squared plus 1. So the Laplace transform of h of t, which is equal to the integral, that's our problem, so I wrote that out, this Laplace transform is equal to f of s times g of s. So I have 1 over s plus 1 times 1 over s squared plus 1. So this is our final answer here. We talked about properties of the convolution integral, and two properties that were kind of interesting is that f convoluted with 1 does not equal to f, and f convoluted with itself may be negative. We talked about applications of the convolution integral. In particular, when solving differential equations, we in other chapters we would take the Laplace transform, we'd convert our problem to an algebraic problem, and then at the end we would take the inverse Laplace transform. And so we would use our convolution theorem whenever our inverse Laplace transform had contained a product of two other functions that were also Laplace transforms. Then last, we talked about the transfer function and impulse response. And we investigated this by looking at a second-order differential equation equal to a forcing function, and we let that forcing function equal to the Dirac delta. So that's it for this video. Thank you for watching.